right? So beginning of chapter 5, dealing with our quadratic functions. Our 5 objectives here are being able to recognize a graph of a quadratic function. So think of parabolas, U-shaped, or hills. Being able to find the axis of symmetry, our x equals negative b over 2a. Again, we'll define these more formally in a moment. And the vertex of a parabola. So usually we use the variables h comma k, but your vertex, your h is really negative b over 2a, comma, and then you plug that into your function as your x value to figure out what your y value is. So these are two representations of calculating your vertex of a quadratic function. And then we have finding the intercepts of a parabola, whether it's your x-intercepts or your y-intercepts. Being able to graph a quadratic function. And then finally, solving your maximum and minimum application. So are we dealing with a hill or are we dealing with a dip? If it's a dip, we have a minimum. If it's a hill or a mountain, then we have a max. So first objective, recognizing the graph of a quadratic function. Anytime you're looking at a polynomial, it's essentially the highest degree is a 2. That's why you have second degree polynomials are synonyms of quadratic functions, which is a synonym of a parabola. And so we have a few different forms here. I think you guys are most used to the general quadratic form, which is our whole ax squared plus bx plus c. But then we also have our standard form, which is our a in parentheses x minus h squared plus k. And I kind of call this vertex form because you're very easily able to identify what your vertex is from your standard form. It's again your h comma k values. And then last but not least, your h is another way of stating your axis of symmetry, which can be found by computing negative b over 2a from your whole general quadratic formula. So all of these are very, very useful. And then when you're finding the domain and range of a quadratic function, your domain of quadratics almost all the time is going to end up being all real numbers because you have no restrictions with your x values, but your range is always going to have that restriction, whether you're dealing with a maximum value or whether you're dealing with a minimum. Okay. So let's jump into our first example, where we have x squared minus 4x plus 4, and it's given to us in standard form. So what does that mean? We can very easily identify what our a, b, and c values are. Our a is just 1. Our b is the coefficient of our negative 4x, which is negative 4, and then our c is always our constant, which is 4. And then we want to identify the vertex, domain, and range of the function. So vertex is always found using your axis of symmetry. And the formula for our axis of symmetry is negative b over 2a. Our x value, aka our h in our vertex, is equal to negative b over 2a. And we have our b's and a's off to the side here, so we're just going to plug in. And so we get negative, in parentheses, negative 4 over 2 times 1, which ends up being a positive 4 divided by 2, which is just 2. So we just found our h value in our vertex. Now we need to find that k. And how do we do that? All we have to do is plug in that 2 into our function. So we have 2 squared minus 4 times 2 plus 4. And when we solve that, that will give us our y coordinate, our k value. So we have 4 minus 8 plus 4, which ends up just giving us 0. So our k is 0. Therefore, our vertex is just 2, 0. And then the last part is being able to identify the domain and the range. And so if you look at your a value, our a is greater than 0, which is important because then we're looking at a quadratic function that is u-shaped and has a minimum value. And that minimum is at our vertex, 2, 0, which helps us with solving for our range. The smallest possible y value is 0, and then there is no max, so it shoots up to infinity. Whereas, what do you think our domain is? Do we have any restrictions for our x values? We do not. So our domain is all real numbers, negative infinity to infinity. And we're done. Any questions on this one? Yeah. Either the lowest point or the highest point. If this is less than 0, your a value, then you're going to be looking at like a mountaintop and your vertex is going to be that max. Yeah. Okay. So that really just leads us into this next slide, dealing with your vertex either being the absolute minimum of the function or the absolute maximum of the function. Both of these are known as your vertex. It's just in that first example, our a is greater than 0, and so we have a minimum here. Whereas in the second example, our quadratic function's upside down, our a value is less than 0, and we're dealing with a maximum. And so on a lot of exams, quadratic functions questions are broken into certain parts, and usually part A is always asking, is your quadratic function opening upward or downward? All you have to do is ask yourself, okay, my A, is it negative or is it positive? If it's positive, then it opens upward. If it's negative, then it opens downward. And that's it. So that's essentially what's exactly being said down here, just more formalized. So now knowing that, let's look at example 2 where we're asked, does Part A, parabola open upwards or downward, and then same with part B. So again, just look at your A value. Our A is -3 for part A, whereas our A is 6 for part B. Is -3 positive or negative? It's negative, so it opens. Remember, it's upside down. Yeah. Opens downward. 6 is positive or negative? Positive. So, yeah, opens upward. Our objective 2, we spoken about it a bit, but now here are the formalized definitions. Our axis of symmetry and vertex of a parabola. So again, axis of symmetry is our whole x is equal to -b over 2a. And this represents your h value in your vertex, h comma k. And then how do we find our k value? We just plug this h value back into your function in order to spit out that k. Again, a vertex can be either the minimum or the maximum. It's just that dip or that peak. It's where your parabola changes from decreasing to increasing or vice versa, increasing to decreasing. So in example 3, we're asked to calculate the axis of symmetry, find the vertex, and then find the domain and range. Very similar to our example 1. So again, part A, axis of symmetry, x is equal to -b over 2a. This is our h coordinate point of our vertex. And so our A is 3, our B is -6, our C is 2. Plug this in, we get negative in parentheses -6 all over 2 times 3, which is just the same as +6 over 6, which gives you 1. So our axis of symmetry is just x is equal to 1. Which from a visual standpoint is a vertical line. And you'll see it a bit more when we start graphing these quadratic functions, but it's the vertical line that cuts your parabola exactly in half. Hence, axis of symmetry, right? Symmetrical on both sides. Which is why if you plug it into that vertex or that original function, you'll end up getting that y coordinate point, aka your k value of your vertex. What we have in pink here is your axis of symmetry. Part B, now we want to calculate the vertex. So how do we do that? We have our h value. So we just plug in that h, which is 1, into the original function, and then compute. One squared is 1, times 3 is 3, 6 times 1 is 6, plus 2. So we get -3 plus 2, which gives us -1. Therefore, our vertex is just 1, comma, -1. And because our a value is positive, right? 3 is greater than 0, we're looking at a U-shaped parabola, which means we have a minimum and so when we're looking at our range, our lowest possible value is at that y coordinate of our vertex, which is -1, and there is no maximum, so it shoots up to positive infinity, whereas our domain, we have no restrictions, so we once again have all real numbers, -infinity all the way up to positive infinity. And that concludes this problem. Any questions at all? Let's do another example. This is going back to what we were practicing yesterday with finding inverses of functions and restricting the domain. So we have a quadratic function here. If you wanted to sketch it out very briefly, practicing your knowledge of transformations. This is in our standard form, and so aka our vertex form, which tells us that our vertex here is just 2, -3. And then our a value is out in front, it's just 1, which means it's going to be a U-shaped. And then we can add in one more point. Why don't we do our y-intercept, which is just when x equals 0. So we get -2 squared, which is 4, -3 is 1. So 0, 1. That way we can do the whole axis of symmetry. Right? Because your axis of symmetry is always straight through your vertex. Okay. So that's your sketch of your original function. And then we want to find the inverse. So again, we're going to end up restricting our domain. And I'll show you where it's restricted after we calculate the inverse. But think about our regular quadratic function, x squared. When we find the inverse, we're looking at the square root of y, or ends up being the square root of x once you switch back, which is plus or minus square root of x. And we end up excluding that bottom part. So we're really just looking at positive square root of x. So essentially it's going to be the same thing. It's just now we have this horizontal and vertical shift taking place. So how do we find the inverse? Again, we write everything first in terms of y. So our y is equal to, in parentheses, x minus 2 squared minus 3. And then we swap our x and our y. So we're now looking at x is equal to, in parentheses, y minus 2 squared minus 3. And now we want to isolate our new y. So let's first add 3 to both sides. And so now we have y minus 2 in parentheses squared equals x plus 3. And then we can go ahead and take the square root of both sides. This is really where the restriction comes into play, because we're just going to hone in on the positive square root of x plus 3. And then last but not least, we're going to add 2 to both sides. So we end up getting y is equal to our positive x plus 3, positive square root of x plus 3, and then plus 2. But you don't want to forget to put it into your proper inverse function notation. Right? And so if we were to sketch this out on our graph, we don't have to, but I'll just do it so you have a better idea of what's happening. It's going to be -3 comma positive 2 as your starting point. So 1, 2, 3, 1, 2. And then you're essentially just doing that top part. And you're done. Questions at all? Yeah. Yeah, because remember, your general form is always going to be x minus h squared plus k. Or in this case, we're just dealing with x, the square root of x minus h plus k. And there's a plus 3 here. So it's really x minus -3 plus 2, which tells us that point is -3 comma 2. Yeah.
That would be the final answer. You don't have to like write them in.
You don't have to write the what out? No, you don't, because it's just saying we're restricting the domain and then we find the inverse. So you're just finding the inverse of the function. Yeah. By restricting it, by not including that bottom part. Yeah. We actually didn't even have to graph this out. I just wanted you guys to see it visually. Yeah. If they specifically ask you, to state the domain restrictions, then you would have to include that too. But you don't have to here. And a lot of the time, I would say when you're asked to find inverses of functions, they'll state it in the problem what your domain restriction is. Okay. Third objective, finding intercepts. Y-intercept is very straightforward. You just, wherever you see an X, you plug in 0 and then you solve for your Y. X-intercepts are a little bit more tedious, but not too bad. That's where you're really factoring a quadratic, or you're using the quadratic formula and you're finding those zeros, aka roots, aka x-intercepts, which is just essentially when y equals 0. They're just opposites of one another. And so that's what we have written down here more formally. So now knowing that, why don't we look at example 5 and find the intercepts of this quadratic function? So again, your y-intercept is very straightforward. Ends up being, if it's in your general equation form of a quadratic, it's always going to be just your c value. right? Because if you plug in 0 for all your x's, the first two terms end up canceling out, and so you get your y-intercept to just be -8. As a coordinate, it's just 0, -8. Your x-intercept, again, involves just a few more steps. It's when y is equal to 0. And so you essentially have your function x squared minus 2x minus 8, set that equal to 0, and then we ask ourselves, can we factor that left-hand side? Lucky for us, we can. Can factor it into x minus 4 and x plus 2. And then that will give us our x-intercepts when we set those equal to 0. We get x is equal to both -2 and +4. These are our x-intercepts, which means in coordinate form, this is -2, 0, and 4, 0. And then we're done. Bless you. Questions? Right. And now we'll jump into discriminant. You have learned about this a bit in Math 190. Our whole b squared minus 4ac, which is essentially what falls underneath that square root sign when we're looking at our quadratic formula to find x-intercepts. So just to review your knowledge of your quadratic formula, we have x is equal to -b plus or minus square root b squared minus 4ac all over 2a. And again, that discriminant is what falls underneath that square root sign. And so it's really important because anything underneath a square root sign has different cases. If it's 0, then that plus or minus square root of 0 is just plus or minus 0, which means you no longer have two different solutions. You just have your solution of -b over 2a. And so that gives us our middle case here, where you have one solution, aka one x-intercept, but that solution is a multiplicity of 2. So I like to write one solution with the multiplicity of 2 because that root, that intercept, is being repeated twice. And that visual, that one x-intercept, it's just bouncing off the x-axis. So that's another phrase that I like to use. Anytime you have a multiplicity of 2, it bounces off your x-axis.
What is the multiplicity?
Yeah, multiplicity is just the root is being multiplied. It's being repeated. All quadratic functions will always have two roots, but a root can be repeated twice. And a good example of that is like x minus 3 squared. That's a quadratic function, right? If we FOILed this out, we would end up getting x squared minus 6x plus 9. And that x minus 3, well, our x-intercept is x equals 3 and x equals 3. Oh, we have one of the same root, one solution, but it's repeated twice. It has a multiplicity of 2. Yeah. And so that's why it really bounces off that x-axis, because it hits it there, and then it hits it again there. So that's one case dealing with our discriminant. Let's look at another case. I'll just erase this to give you just more clarity. Another case is, what if we had a real number in here? So what if this whole b squared minus 4ac, I'll pick an easy one, is 16, because we can very easily take the square root of 16. Square root of 16 is 4. Well, now we have negative b plus 4, and we have negative b minus 4 all over our 2a. That's going to give us two different solutions, two distinct real solutions, which means you're going to end up hitting that x-axis in two different locations. So anytime your b squared minus 4ac is greater than 0, you're going to have some value here that when you compute this with that plus or minus, you get two distinct solutions, aka two x-intercepts. And then finally, the last case is when you enter into the imaginary world and you have your b squared minus 4ac is less than 0. So the square root of negative 4 ends up being 2i, 2 imaginary, which means we're no longer in the real number system. So we will have no real solution here, which means if there's no real solution, it will never hit your x-axis. So there'll also be no x-intercept. And so x-axis is never hit when we have imaginary numbers involved. That's it. Yeah. Questions at all? Again, these are our three cases, case 1, case 2, case 3. Okay. So let's do example 6, where we are asked to find the intercepts of the parabola whose function is 5x squared plus x plus 4. Again, let's start with the easy y-intercept. So look at your constant. So our y-intercept is just 0, 4. Done. X-intercept. This is where we want to factor, if we can. Is this factorable? We're going to have to use our AC method here to see if this works. So our A is 5, our C is 4, so factor pairs of 20 that add up to 1. Don't think it's possible, right? Because it would have to be 5 and negative 4, but then that would give you a negative 4. So let's attempt our quadratic formula. I have a feeling it's either going to involve square roots or it's going to be imaginary based off of us learning about discriminates on the previous slide. So x is equal to negative b, which is just -1, plus or minus, and I'll put your a, b, and c over here so you could follow along. 5, 1, 4, plus or minus square root. B squared is just 1 squared, which is 1, minus 4 times a times c, all over 2 times a, which is 2 times 5, which is 10. Let's simplify. We have 1 minus 20 times 4, which is 80. Yeah, it's negative. So x is equal to -1 plus or minus square root of -79 all over 10. Because it's a negative underneath the square root, what do we have? Imaginary number, which tells us what? Yeah. Therefore, no x-intercept. Yes. How did I get 80? So let me just make sure I did it right. Your quadratic formula is x equals -b plus or minus square root b squared minus 4ac all over 2a. And then I just plugged in my a, b, and c values. So b squared is 1 squared, which is 1, minus 4, and then a times c is 5 times 4. So 5 times 4 is 20, and then 20 times 4 is 80. So then we get 1 minus 80. Yeah. 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 You always want to start out with, okay, can you factor it? Because that's the easiest way. And then if you can't, then you're like, all right, quadratic, because quadratic will always get you the answer. It's just you never want to lead with quadratic because it's more tedious. Yeah. All right. So we're finally on to our objective 4, dealing with graphing quadratic functions. But we've done some practice with it. It's just really putting everything all together now, understanding, oh, is our a value positive or is it negative? Is it opening upwards or is it opening downwards? What is that axis of symmetry that folds that parabola in half? And using that axis of symmetry, can we find our vertex? Can we find our minimum value or our maximum value? Now we have that, let's plot some other points. Let's find our intercepts. Our y-intercept is just our constant, so we can plot that. But now, since you have that y-intercept, you can use that axis of symmetry to reflect it over on the other side. So now you have a beautiful sketch. But why don't we also put in some x-intercepts? And do we have x-intercepts? How do we determine that? We use our knowledge of discriminant. Is it less than 0? Is it greater than 0? Or is it actually equal to 0? Put all of that together and boom, you have your graph. So let's practice. We're asked to graph this function -x² plus 6x minus 9. And then once we finish graphing it, we want to state the domain and range of our function. So I'm going to bring in the graph so I don't have to label. Mathematicians are inherently lazy. Take the simple way through life. Okay. So first step, let's analyze our A. And we can write out our A, B, and C off to the side. Our A is -1, our B is 6, and then our C is -9. And so is our A positive or negative? It's negative, which means, yeah, it opens downward. It's going to look something like this. Okay, first step. Second step, axis of symmetry. So our x is equal to -b over 2a. You get -6 over 2 times -1, which is just -6 over -2, which gives you 3. And this is your h value. And now we want to find, and again, I'll maybe label this as axis of symmetry. Should probably just group it as well. I always like to graph it by like a dashed line. So that's where it splits in half. And we're gonna label it x equals 3 in parentheses axis of symmetry. Okay. Now let's find our vertex. How do we find our vertex? We just plug in our axis of symmetry. Right, we want to find that k value into our function. And so we're looking at negative in parentheses 3 squared plus 6 times 3 minus 9. Be careful that negative in the beginning is not part of the parentheses. So it's going to end up being a negative value for that first term. 3 squared is 9, so then we have -9. 6 times 3 is a positive 18, and then minus 9. So we end up getting 0 for our k value, which means our vertex is 3, 0. So we're going to plot that. And that vertex, because it opens down, that's going to give us our max. Now let's plot some intercepts. Our y-intercept is just our constant, which is -9. So as a coordinate point, we have 0, -9. And now we know our axis of symmetry, so we can reflect that. It's 3 units to the axis of symmetry, so another 3 units out gives us another coordinate point. And we have enough information now because that orange dot, that vertex is our max, and it happens to be on our x-axis, then we just have one real root with a multiplicity of 2. It's bouncing off that x-axis. And so that real root is 3, aka our x-intercept. If you wanted to write your x-intercept out here, you could. 3, 0. And so we graphed out our parabola. We want to make sure we label it. It's our -x² plus 6x minus 9. And then our last part is we want to state the domain and the range. So our domain, again, there are no restrictions here. So we have all real numbers, -infinity to +infinity. And then our range has that maximum value at 0, but we have no minimum. So it's negative infinity all the way up to 0, hard bracket. That's it. Yeah. This part you're saying?
Yeah.
Yeah, I just literally just counted. We knew that this was a y-intercept, and we know that this is the halfway point. So I just counted 3 units to that line of reflection, aka that axis of symmetry, and then I just from here counted 3 because they have to be symmetrical. Yeah. Okay. How do you guys feel about this? 1 to 5. Okay, cool. Nice. Great. Right, let's do another example together. Feel like we're almost done. Yeah, we have 3 more examples from this slide or this lesson. So same exact procedure, but we'll just speed it up a little bit. Put in our graph. Is it going to open upwards or down? A is equal to 1, which is greater than 0, so opens up. I'm going to put in B equals 4 and C is equal to 5. Our step 2, axis of symmetry. Negative B over 2A. Negative 4 over 2, which gives you negative 2. Let's plot that out. Step 3, vertex. F of negative 2 gives you negative 2 in parentheses squared plus 4 times negative 2 plus 5. So we get 4 minus 8 plus 5, which is just 1. Therefore, your vertex is negative 2, comma 1. And that's going to be your minimum value. So straight off the bat, you know that the discriminant is negative, right? It's not going to hit your x-axis. So x-intercepts, we have none. Just visually looking at it. And your y-intercept, again, is just your constant, which is 5. So as a coordinate, 0, comma 5. And then we can reflect that y-intercept. It's 2 away from your axis of symmetry, so let's do 2 in the other direction. So that's another point. So that we have enough points to graph out our function. I always make it like a V, but it should really be a U. And then you don't want to forget to write out your function f of x, label it equals x squared plus 4x plus 5. Last part, identify your domain and range. Domain, once again, there are no restrictions for your x. So we have all real numbers, negative infinity to positive infinity. Range, you do have some restrictions. Your minimum value is at 1. So it's going to be hard bracket 1. And then there is no restriction on your max. So it shoots up to infinity. And that's it. really like a 5-step process. I want to go through all of it. Questions? No. This one I feel like is the same x squared plus 4x plus 5. Yeah. So, my boss told me, he was like, if you find any mistakes, just let me know so I can revise them. So, same as previous example. So the last objective for this section is just dealing with your maximum and minimums, but I feel like you have a really good grasp of this at this point, because essentially if your A value is positive, you have a minimum, you have that U-shaped, and if your A value is negative, then your quadratic is upside down and you have that maximum value, and you determine that through substituting in your axis of symmetry to find what your exact minimum or maximum is on your coordinate plane. So that's essentially what this whole slide is saying. And this last example is just finding the minimum or maximum value. It's a very common question that I tend to see on midterm exams as well as final exams. So again, you identify your A, B, and C. You really don't even have to identify your B and C for this first part because we just want to look at your A. And because if your A is greater than 0, we have this U-shaped, then we're looking at a minimum that's taking place. And now we want to use that B value and the A in order to determine what's that exact point, utilizing your axis of symmetry, negative B over 2A. So we get negative 2 over 2 times 1, which just gives us our axis of symmetry to be negative 1. And then last but not least, we want to plug that into our function again so that we can find that minimum y value, aka the vertex point. So we get negative 1 in parentheses squared plus 2 times negative 1 minus 8. That just gives us 1 minus 2 minus 8, which gives us negative 9. So our vertex is just negative 1 comma negative 9. But again, when you evaluate the minimum or maximum, you just clearly look at that y value. So your final answer is minimum at negative 9. Or you can say minimum at y is equal to negative 9. And that's it. Questions? So that concludes our section 5.1 dealing with quadratic functions. The next topic is going to be our power functions, polynomials, and their graph.